Hello everyone, welcome back to another Learning Glass video. So, today we'll talk about nuclear power in the form of the current technology, which is nuclear fission, versus the upcoming, hopefully soon to be implemented, nuclear fusion. So, one is currently proven and well established and still making an everyday impact in our lives. So that is nuclear fission is what we currently have versus nuclear fusion, which has been studied for the same amount of time. It's just no one has been able to get it to work and make a big impact in terms of everyday applications. So this is proven everyday, how do you spell everyday? Proven everyday use for weapons. Thankfully, the weapons are not used every day, but they exist every day. They're on call every day, on standby every day. It might happen someday, hopefully not. Power plants every day. We have a nuclear power plant powering electricity to a big grid in some city all throughout the world. And also nuclear medicine. We've been taking advantage of the fact that some materials they split to create some nuclear reactions that can be used for medicine. As opposed to nuclear fusion, it has only proof of concept. We've been able to get it to work in the lab on the prototypes, but there's no successful, no scalable applications yet. So we know it can work. We've been able to tinker with it in the lab successfully, but we haven't been able to make weapons out of it, power plants out of it, or medicine from it yet. Fission we have. And we'll explain what what is fission? Here it is here. Fission, we split larger atoms, then what happens is you get smaller atoms plus some energy. As opposed to fusion, where you fuse, instead of fizz and split, you fuse, where you start with smaller atoms, then you fuse into larger atoms plus energy. Fuse smaller atoms into larger atoms plus energy. And as opposed to electron chemistry or just everyday chemistry, these are nuclear chemistry, nuclear reactions, and in one huge difference between nuclear reactions and normal chemistry is that we're changing the atoms. Instead of changing the bonds to keep the atoms with different molecules, different bonds, you're changing the atoms. And when you do that, energy no longer becomes conserved and mass no longer becomes conserved. Why? Because they can interchange in between each other. How? By Einstein's equation. That energy can go between mass and so forth as by this equation related to the speed of light. Okay, so that's fusion versus fission. Fission, we're doing everyday applications, splitting atoms to do these things. Some of the energy can go to mass and back and forth. Fusion, trying to go from smaller atoms to larger atoms, works in the lab, but we haven't been able to fully scale that up for power supplies and everything else like that. And here, another big difference is that there is nuclear waste. So produces fission, produces hazardous, dangerous, radioactive waste. And if we ever did get fusion to scale up for everyday use, one potential benefit would be potentially, not in every scenario, but the goal is potentially to no dangerous radioactive waste. Radioactive means it gives off radiation, high energy, that can damage living things. It does a lot of damage to everything around it, especially living things. And fusion, if we're able to design an optimal system, will give you none of this. And we'll talk later that there is one scenario of fusion just as a byproduct of like some indirect reason that it can potentially produce radioactive waste. Okay, so these are nuclear reactions, as I said. So nuclear fission, nuclear chemistry, nuclear reactions these involve changing nucleus, which is protons and neutrons, to form new atoms. Meaning that you started off as a certain atom, and then it's going to change by the different protons and neutrons to form new atoms. And most everyday chemistry, by default, like everyday food, life, burning of fuel in the engines, most everyday chemistry only involves electron cloud. So atoms are conserved in everyday chemistry. Energy is conserved, mass is conserved, and even the atoms keep the same. Only new molecular bonds are formed. So new molecules are formed. Bonds change. So the energy stays the same from the beginning to the end. The mass stays the same from the beginning to the end. The thing that changes is the bonds formed by the electrons surrounding it. That's the vast majority of chemistry on Earth in our everyday lives. If we look into the sky, we see some bright lights, some high energies. Sometimes the sun, when we feel the sun, it's very hot. That's because it's undergoing nuclear reactions, mostly nuclear fusion. That's, in terms of mass, of course, the sun is more massive, but in our everyday lives, of like biochemistry, foods we eat, processes we do in industry, just our general bio ecosystem, that's just all electrons and molecular bonds formed, as opposed to changing the atoms. Okay, so in terms of nuclear chemistry, we still have a lot of applications with nuclear fission, where we split the atoms and we can apply that for nuclear weapons. Thankfully, we haven't, it's been about 80 years since we dropped nuclear weapons, and ever since then, they've been on standby. Thankfully, nothing has escalated to nuclear war. And but they exist. They're always a threat. They're always going to be a part of our society. Another one is for peaceful purposes, you can use nuclear fission for a nuclear power plant. And nuclear fission requires a certain set of fuels that are that naturally undergo nuclear fission, and then we can use that in a nuclear power plant. What are those fuels? They are fissile materials. So nuclear fission for nuclear fission, you need fissile material for fuel, meaning that it readily splits into smaller atoms plus energy. It turns out, what are fissile materials? Pretty much a lot of big atoms are fissile materials. Big atoms are not as stable as smaller atoms, and some of them, they're so unstable that they naturally decay by a nuclear reaction that forms different atoms and gives off energy as well. And that, most of the time, that energy is dangerous and damaging to everything around it, including especially living things. Like if it was just a material, it'll cause radiation damage, it'll seriously mess up the structure of that material. And imagine if this is a living tissue, it would do even more damage. Okay, so nuclear fissile material. One big example, it's uranium-235. What is uranium-235? Well, if it has a core of in its nucleus, within that nucleus you have protons and you have neutrons. You have protons and neutrons, that's the nucleus, and then you have its electron cloud with all the electrons. So uranium-235 has 92 electrons in the cloud, 92 protons in the nucleus, and 143 neutrons in the nucleus. So it has way more neutrons there, or it just has a lot of neutrons there, and it turns out this certain combination of the nucleus and the electrons with this amount of neutrons makes it unstable such that it's a fissile material. It'll split. And especially if you were to excite it or bombard it with some neutron let's say that you shoot it with a neutron exciting, you bombard it, you shoot a neutron shoot a neutron into this, you'll start a fission process. Then you'll have an extra neutron. So it started off as 235 as its mass number, and then with this neutron it's going to be 236, and that's an unstable thing where you form new atoms. You'll form krypton 92 and barium 141, and you'll form 3 neutrons. So this is how you're starting a chain. By shooting in one extra neutron, you create this even more unstable fissile material, uranium, and then that naturally splits into these new atoms and energy and more neutrons. When you have more neutrons there, you can supply even more of this fission. So then you can, cause a chain reaction where in this direction you're going to be forming lighter atoms and more energy is going to get released. So here you can form, maybe go again to U235 again, or you can start to form even lighter atoms. Then you can, just keep on, it's called a chain branching process, where you have, because of these neutrons get multiplied, and there's energy releases at each step, you have more energy that can be explosive. So this is the chain reaction process. So if you are, it gets just really, really hot, and because it's hot, it wants to expand, and that can be dangerous for if you don't want it to. So if you're going to apply this to a nuclear bomb, this is where the explosive thermal energy comes from. If you want to turn this into a nuclear power plant, you need to control it so that this reaction stays within your power plant, that you can harness it as designed to take advantage of this thermal energy without being explosive. You need this chain reaction to keep the energy going, but you have to moderate it so that it doesn't go out of control and have this thermal runaway where you just keep on producing more and more neutrons. Those neutrons burn the original fuel, fission the original fuel, and fission all these other light atoms and keep on multiplying neutrons. You need to moderate that so that it doesn't have thermal runaway or nuclear meltdown. So that's a very important part of nuclear power plants. And there's a lot of energy released in this each time you do this process. Okay? So then what you do when you have this energy release, so how does a nuclear power plant work? Well, nuclear power plant is actually very similar to an old-fashioned combustion engine power plant. There is a couple of ways to burn a fuel to make a power plant. The two major ways to make a power plant by burning normal fossil fuels is to use coal and run a steam power plant called the Rankine cycle. Another one is to burn natural gas in a turbo machinery set of stages in a Brayton cycle. So both of these are power cycles that are heat engines. you have to take an source of high temperature energy to, in a cycle of stages that are a closed loop that keep on repeating, starting from a high temperature source of energy. So for a coal power plant, you burn the coal. That coal allows you to boil water. That high temperature, high enthalpy steam allows you to turn a turbine, and then you keep the cycle going into so that you can get the steady output of energy from the burning the coal, boiling the water, turning the turbine. Then you pump the water back into in a Rankine cycle. With the natural gas Brayton cycle, you take in this fuel-air mixture of natural gas, you burn it internally, internal combustion engine. Those combustion products go to turn the turbine blades. So that high temperature combustion products gives you high enthalpy that you can turn into a turbine to get mechanical work, and then you keep the cycle going. Those are awesome, those work for power plants. That's how we get our electricity in throughout the most of the world. The problem with that is that you lose a lot of the energy. You lose most of the energy to the exhaust. That high temperature source of energy, only about 50% or less gets extracted into mechanical work. The rest gets ejected into the surroundings. That's just the second law of thermodynamics. That's what we're dealing with. That's the same problem with this nuclear fission reactor. What you do is you run a heat engine by this heat from the reactor. So this is the fuel at the this would be a reactor. That reactor, like the top where it's holding the control rod, is a very important part of this whole design, is control rods, because like I was saying, you need to somehow moderate these neutrons from giving off too much energy, because it'll just keep this chain expanding and chain branching and eventually become explosive and uncontrollable. So a typical reactor would have a tank of water, moderator water. This would be another way to keep the neutrons contained. Moderator water. These are control rods to also absorb the neutrons. And here is the reactor core, where you have the fuel elements of uranium getting bombarded, or like, you know, the neutrons, once you start going, the neutrons come in, but once this is going, you have a steady supply of neutrons coming off of this thing. So you need the moderator and the control rods to make sure you don't have thermal runaway, chain branching, chain reactions that are uncontrolled. If it's uncontrolled, it becomes a nuclear bomb. If it's controlled, then you can run a heat engine. So for the power cycle, the nuclear power plant, what you do is you have a heat exchanger where you're able to somehow interact such that you can bring water in, a separate stream of water. This is a pool of moderator, but there's some heat exchanger in between where indirectly you're able to interact with this high temperature reactor core. So the heat exchanger will allow you to produce steam going out. Then you have another separate flow where this is a boiler of separate stream of water, where it's a high enthalpy out, meaning high energy coming out of the boiler, then you're able to feed a turbine where you get mechanical work out and electrical generation, electricity. But to keep the cycle going, you have to exhaust a lot of that energy, condenser, and you have to pump it back up. So you have to put work in. So it's a continuous heat engine, which is good because it's a compact way to get a lot of mechanical work from this high temperature source. So the whole point of this is that it's a heat engine at the end. It's not a nuclear engine. It just uses the nuclear reactions to get a high temperatures enough to boil water. Once you have that boil water that's a high enthalpy, you can use that to transfer from high enthalpy to lower enthalpy, giving you some mechanical work at the turbine where you can make electricity eventually. But this nuclear fission reactor, splitting this atom of the uranium, is just the high temperature reservoir for a conventional heat engine, namely the Rankine cycle. Again, that's a nice source of energy, but one big downside to these heat engines, which we rely on, we have a nuclear power plant, one remaining in California, a few throughout the United States, many throughout the world, is that it's a heat engine. By the second law of thermodynamics, you're going to lose a lot of that energy to the exhaust. This is an exhaust. It's called a condenser specifically, but you know, it's just something, it's a heat out. So you get heat in. So it's heat in. That's the energy came in. That's where all the energy comes in. Some of it goes to mechanical work, but actually most of it gets lost here. Why? Because it's a heat engine. That's just the way that we've been running. Our technology is based on burning a fuel to get a high temperature, to get mechanical work somehow, but most of it gets lost because we're in a heat engine power cycle. For natural gas Brayton cycle, we burn natural gas to get an internal combustion, high temperatures, and we get mechanical work, but we still have to lose most of that energy. We haven't been able to avoid this. Even with the nuclear fission reactor, we have this nice reactor core giving us this high temperatures that allow us to boil water in a Rankine cycle, but we still lose a lot of that energy. So, okay, that's nuclear fission. That's the current everyday power plants that we have. The question is, how does this compare to nuclear fusion? So now moving from nuclear fission to nuclear fusion. Nuclear fusion. It's no longer big atoms going to smaller atoms. It's the smallest atoms, as a matter of fact, going into larger atoms. So fusion, you know, we've been playing around with it as long as we've been playing with nuclear energy in general. It's just that it's harder to get to work than nuclear fission. No one has been able to successfully scale up and implement a lot of these ideas of nuclear fusion. Nuclear fission has had a lot of success. So that was our fusion reactor. Okay, so what is the strategies moving on to the future technology? Hopefully someone eventually figures this out. There's three, so nuclear fission reactors. I have four general strategies here. Nuclear fission reactors. I'll just list them here. We have a tokamak strategy. We have a stellarator strategy. We have an inertial confinement strategy. And then there's another one I'll just call Helion. I'll elaborate on it later. So those are the type of reactors. Interestingly, for three of these, they're still limited by heat engines. So the idea would be that if someone was able to get a tokamak design working, the design plan would be to use the tokamak to power a heat engine. Similarly with the stellarator. The stellarator is meant to power a heat engine. Same with internal confinement and inertial confinement. It's made to power a heat engine. So the tokamak or stellarator or the ICF, let's call it, those are meant to be the high temperature source for a heat engine. Which is, I guess, fine, if we can get a better way to get high temperatures, we know that a heat engine would work. We know how to work with heat engines. The downside is that we're going to lose most of that energy and heat out. We're going to take a huge loss here. But that's just the way we've been relying upon. No one has been able to get a better way. We tried solar cells. Solar cells are good, but we don't have a huge citywide power plant based on solar cells. It's not enough. We need a high temperature thermal reservoir like burning a fuel or a nuclear reaction to power a whole city. We're trying with solar cells. It's not enough energy yet. We had blackouts a few years ago depending too much on solar cells. Batteries, still not big enough to store enough energy to rely upon as our base load. Wind power, still not enough to supply our base load. Maybe if we had a humongous hydropower plant, a big waterfall, that is very good. But there's not a lot of big waterfalls throughout the world. There's only a few, and those are pretty good, but they don't come easily everywhere across the world. So the idea would be to use a tokamak fusion reactor, a stellarator fusion reactor, or an inertial confinement fusion reactor to get this heat engine going. Okay, so more specifically, let's talk about all of these require currently pretty much all of them require fusion. Fusion relies on manipulating plasma fuel. What does that mean? It means that the fuel is going to be a gas phase light atom. Then you're going to energize this fuel by so high that it pops off an electron and becomes a charged electron. So plasma is high energy charged ionized gas. So it has a charge to it. It's either plus or negative. Charged gas. And it's in fusion cases, you need high temperatures as well, but it can also be like moderate temperatures. It's just high enough energy to ionize to make it plus or negative charge. Okay? So, for a stellarator Let's go back to these here. So tokamak, I'll go back down here. Stellarator, what it does, it has a fuel plus plasma. And it's controlled by magnetic field in a torus reactor. What does torus mean? It means a donut. That's a torus. Tokamak. Tokamak is also fuel plus plasma, controlled by electric currents. They're all magnetic, but the difference is that there's an electrical current in the plasma. So there's no current in the stellarator, but there's a current in the tokamak. And it's also a torus. Slightly different shape, but still. Okay, so inertial confinement. It's not a torus, no more donut, but it's surrounded by lasers. So inertial confinement, it's fuel plus lasers. So you don't start with the plasma directly, you start with the fuel, but the laser beam causes an implosion because by directed laser field. So you get all these lasers pointing at the fuel. That's so accurate how all these lasers are shooting in the same opposing directions that it causes the fuel to implode and fuse. Helion is different. It's a reverse field configuration. So let me erase these, this heat engine here. So Stellarator, Tokamak, and ICF are designed to power a heat engine. But Helion, the plan is for the Helion reverse field configuration reactor to bypass the heat engine, because the whole point of the heat engine is to make electricity. I mean, you can power a plane to get propulsion, thrust, or you can make a power plant to make electricity. And for the electrical applications, the Helion reverse field configuration, inertial confinement, our magneto-inertial approach by Helion is going to bypass the heat engine such that when you have this charged plasma in the reactor, that charged plasma is going to be able to give you an electrical generator such that you have a direct fusion reaction to electrical generation approach that bypasses a heat engine. So that's the major difference between these other ones supporting a heat engine to the Helion that's going to bypass that. So Helion is the name of a company. but just an easy way to remember which design this is. And I have, we're going to talk about this in lecture, and we have some videos that are nicely done to talk about all this stuff, especially the Helion one. Reverse configuration, which is a magneto inertial approach. So what you do is you still have plasma plus fuel. Plasma plus fuel controlled to collide opposing plasmas. So instead of a donut, it's a counter flow. And then they merge in the middle to create the fusion. And the idea is that you're going to have direct fusion to electrical generation. That's the Helion approach. Okay, no heat engine. These all have heat engines. So again, these are heat engines, meaning once you have the plasma achieving high temperatures, it's going to power a heat engine. This is no heat engine. Because it's no heat engine, you don't necessarily have to lose a lot of that energy to the exhaust. You're not bound by the second law of thermodynamics for that cycle. Okay. So, how exactly do these nuclear fissions work? Nuclear fusion. Well, instead of having a big atom of fissile material, we're going to have, starting from smaller atoms, fusing into larger atoms, releasing energy. So the small atoms, turns out the smallest ones are hydrogen. Then, for nuclear chemistry, often involves different types of atoms that have more neutrons than they normally do. Normally means that naturally occurring, the most common types of these atoms have a certain amount of neutrons in the nucleus. Many times if something has more neutrons than normal, it is nuclear radioactive. And it can cause a whole different set of processes to occur. So in the case of hydrogen, most of the hydrogen on Earth does not have any neutrons in the nucleus. But if you were to have, there's a small portion like 0.001% or like 0.01%, which is about like 10,000 parts per million. So it's not a tiny amount, but of all the seawater on the Earth, that seawater contains hydrogen in the bonds, in the molecular bonds. Less than 1% of that is heavy hydrogen. What is heavy hydrogen? In this case, it's deuterium. It's another type of hydrogen that has one neutron in the nucleus. Then there's an even more rare. So deuterium is rare, but it's not that rare. But if you had a hydrogen with 2 neutrons in the nucleus, that would make tritium, and that's super duper rare on Earth. But those two, deuterium and tritium, isotopes of hydrogen, actually are the main fuels of all fusion power technology that's planned. Okay, so let's start talking about this nuclear fusion chemistry. Nuclear fusion, again, it's to fuse small atoms to produce larger atoms plus energy, governed by, of course, E equals mc squared, where E is the energy, mass is the mass of their system, and c is the speed of light. Okay, for normal, everyday, conventional chemistry, it's just the electrons. Mass is conserved, energy is conserved. But nuclear chemistry, you have this. Okay, for the nuclear fusion fuel, it's heavy hydrogens. So basic hydrogen, just the basic everyday hydrogen would be labeled like this. It has 1 proton, 1 electron, and 0 neutrons. And its molecular mass is 1.007 grams per mole. So that's how most of the hydrogen on Earth molecular bonds exist. Then you have deuterium. So you have these heavy hydrogens. There's 2 different types. One is heavier than the other. Then you have deuterium, which is also a hydrogen, but it's labeled like this because it has 1 proton, 1 electron still. The difference, though, it has 1 neutron in the nucleus. And another symbol for this that you see around is D. D, deuterium. And this, if you get this access to this thing, it's going to be heavier. It's literally going to be double the weight per mole as a basic one. Then, so this is heavy. The other one is heavy too, tritium. T. It also has 1 proton, also has 1 electron, but here you have 2 neutrons. So this is going to be even heavier. So pretty much all fusion reactor designs are centered around these heavy hydrogens. Starting point, we're going to see that helium is also important. Having helium with 2 protons, 2 electrons comes into play when you form these bigger atoms. What is that bigger atom? Helium. And that becomes important too. But the starting fuels is the smaller atoms. So if you're going to use D plus T fuel, a D what will happen is you would have 1D plus 1T. It's not going to form a molecular bond. It's going to undergo a fusion reaction to give you 1 neutron plus 1 helium atom. So this is going to be a new atom. It's not a new bond. It's a new atom. And then you're going to have minus mass. And why? Because the mass goes to energy. So it's going to be E equals mc squared. The mass you lose tells you how much energy you gain. And how much energy is that specifically? It is, here the neutron has a lot of energy, carries with it 14.7 mega electron volts plus 3.5 mega electron volts. That's a lot of energy. And if we're going to use this to run a heat engine, what's going to happen is that this is going to be kinetic, this energy is going to be mostly in kinetic energy, which is proportional to the temperature, which is heat, which can be used for a heat engine. Okay, so there's a lot of challenges to make this work. So deuterium, it's relatively abundant. It's not abundant, but compared to tritium, it's no problem at all. Tritium is the challenge. It's extremely rare. It's so rare that we pretty much have to change up the design to not rely on feeding tritium to the reactor. Instead of relying on a supply of tritium that you can just fill the gas tank with, we're going to have to come up with different strategies to literally produce tritium in the reactor once it's going. So we're going to talk next about the tokamak. What it's going to do, it's going to seed some tritium in there, but once you have this high energy and these neutrons flowing after this reaction starts, we're going to rely on these reactions to give you more tritium to keep the reactor going. So instead of having all the fuel just directly filled in there, you're actually going to have to manipulate and finesse these reactions to make sure that tritium keeps on being produced down the chain. So how does that work? Let's talk about it right now. So the tritium is a challenge because it's much more rare than deuterium. We'll talk about in class one example, and on the other videos we have, it's that literally an estimate of the total supply of tritium right now that we have on reserves, total is 20 kilograms. So that it's like not even my body weight, it's much more than the supply of tritium we have on Earth. I'm like, I don't know, 50, 60 kilograms, 70, 80, I don't know. There's much less tritium on Earth than my mass, which is interesting because if we're going to rely on fusion power, how are we going to get this tritium? Well, here's one solution that the tokamak is going to have to rely on. We'll talk about right now. Okay. Tokamak. It's a type of donut-shaped reactor we got from USSR, and it's one promising solution. So what you're going to do it's eventually you're going to use the fusion reactor to power a heat engine. But to keep the DNT fuel going, so tritium, let's call it T, is super rare. So T will be regenerated. Yeah, that's good. Regenerated. During the fusion process. How? You're going to need breeder blanket to absorb hot neutrons and multiply into more neutrons. That's basically how you're going to do it. You need neutrons to make the tritium. How do you, what is the strategy? You're going to, once you have this supply of hot neutrons, you're going to collide it with this blanket surrounding the core of the fusion to make even more neutrons. When you have more neutrons, you can make more tritiums and get energy. So, how is this going to work? Well, let's say you have this D plus T reaction. These are the two fuels. Then once you do that, you're going to form this hot neutron plus this helium-4. Then, once you do that, this hot neutron is going to be go out. So interestingly, this plasma is going to be confined by the magnetic field. Neutrons are neutral. They're going to go through the magnetic field and hit the blanket. This blanket is going to be made with lithium. Once it hits the lithium, that lithium can produce a tritium plus more helium. Then once you have this tritium, you can keep the reaction going. But this doesn't look very branchy, very chain splitting, chain branching, chain explosive. Why? Because it's more linear than a chain branching. So how do you keep this multiplication chain branching going? You're going to add with beryllium. So you're going to need, so lithium is good, but on top of that, you also need a beryllium blanket. So if you do that, again with this D to T fuel, you do the same thing. The difference though is if you combine this with beryllium, if you do the same thing with beryllium metal, you'll form an excited or like a certain isotope of beryllium that has 4 protons. So beryllium is the atom next to lithium. Lithium's on the salt, the earth metal. Then you have this next set of protons and electrons. Bigger size is next to it, lithium. 4 electrons. Then it's going to have 5 neutrons. And when you make that, it's going to split. It's going to multiply into 2 neutrons. Then The reason why is that's important because one, we're going to need this to make a heat engine. We're still making a heat engine. How do you make a heat? You have to transfer heat from high temperature to low temperature. So when you do this strategy, you can think of it as one neutron going to the heat engine. That's how the energy will go from high temperature reactor to the heat engine to boil water. Then another of these neutrons is going to go to keep on producing more tritium. And then this would be the D. So when you have this beryllium blanket, this beryllium will form you two neutrons instead of one neutron. If you form two neutrons, you can have the source for the heat to power the heat engine, and you can keep this tritium flowing to keep the reactor going. So this is the strategy. Because tritium is so scarce, the tokamak is going to rely on these breeder blankets, namely the beryllium material. That beryllium will multiply the neutrons. When you multiply neutrons, you're going to be able to heat the engine, to have this source of heat transfer going out of the reactor, and also keep this neutron where you can use to make more tritium and keep the reactor going without having to have a supply reservoir of tritium. You have this beryllium blanket, mainly like a supply of neutrons. If you have the supply of neutrons, you can keep this tritium flowing. So that's the strategy with the tokamak. So here, this is beryllium. What I was writing down here is 4 protons, 4 electrons, 5 neutrons. So as we'll talk about in class, this is a good idea. The challenge is that not only is tritium extremely rare, beryllium is also extremely rare. So here, T, so we need to worry about that. Beryllium, metal, it's also extremely rare. That's one huge challenge. Okay, so that's the strategy with the tokamak, and how would that look? It's like kind of like a diagram of this. So this will be like the chemical scheme of how the fuel reactions will be designed. But physically, how would that look? It's going to be a torus, the donut, and then with this field confined. So the temperature of a plasma to induce fusion, it's millions of degrees Celsius. So it's hotter than the temperature of the sun. Okay, if it's hotter than the temperature of the sun, why doesn't it melt everything? It can melt everything. The only way that you can manage it is to use a magnetic field to keep this away from the walls. So it's relatively low pressure, so the mass is not that much. It's gas inside a vacuum chamber. Because it's a vacuum, that means there's not a lot of mass there. So it's very hot, but not a lot of mass. And as long as you keep it away from the walls, it's not going to melt stuff. But you still need a lot of good engineering and design to prevent it from damaging and melting things. Okay, so the idea is, if you have this tokamak, it's a donut. So the tokamak, it's a donut shape where you have this, this plasma going. That's the plasma core. This high energy charged gas that you try to go to high temperatures that will get this fusion, these two atoms to fuse together, which requires an overcoming the repulsion potential of two nuclei. Okay, so this is the donut. Let's go to the side view of the donut. It'll be like a little slice of this donut. Let's call this the plasma core. Plasma core. And according to this strategy here, it's going to have a breeding blanket around it. That's the B, R. Breeding blanket. And what it's going to do is that when you have the neutrons, hot neutrons coming out to the blanket, it's going to hit the lithium and beryllium, and that's going to cause eventually some tritium to come back. So through the solid beryllium and lithium materials, you're going to have some tritium, some exchange between neutrons and tritium. And then some of the neutrons are going to escape, which is the whole point, because these are high temperature neutrons, and that's going to where the heat engine is going to be. So there's going to be another heat exchanger blanket around it. Where it's going to be supply water and steam coming out. And this is going to be the heat engine. And then all of this is going to be surrounded by this, confined by this magnetic field. So that would be the tokamak strategy. You need tritium fuel, and by having these breeder blankets to give you some source of neutrons, some multiply source of neutrons, you'll be able to form more tritium in the reactor, flowing back into the reactor. Okay, so that's the tokamak. There's also the stellarator, and also inertial confinement. But let's now talk about this newer, less established type, but it seems very promising. Let's talk about the Helion reverse field approach. So the Helion is no longer a donut. It's an opposed flow of two plasma balls getting merged together, and hopefully the fusion will be induced after that happens. But the reverse field refers to the fact that you're able to somehow manipulate the plasma such that it's stationary, and then you can manipulate it to shoot them at each other, accelerate them towards each other. Okay. Okay, so the helium has helium has both a different fuel strategy, slightly different fuel strategy, and a different geometry strategy, which gives it a lot of differences. And it also can bypass the heat engine. Okay. So the big difference is that you have D plus D fuel and direct electricity generation. How do they do that? Well, let's start with the fuel chemistry. Let's say we have this D plus D, two deuteriums, two heavy hydrogens in the two isotope, one nucleus, neutron in the nucleus. What can happen there is you'll have some possibility that you'll form a proton and a tritium. Interestingly here, you don't want a tritium. You depend on, it centers on helium-3. Helium-3 fuel. Or it's not even a starting fuel, it's a helium-3 dependent. Helium-3 strategy. Helium-3 strategy. So when you form this tritium here, interestingly here, you don't really want this tritium. It's useful, but you're not going to use it directly. In fact, you're going to use this to store the tritium off-site so that eventually it will decay back to helium-3. So here, the tritium, if you form it, it's not directly useful, except for the fact that eventually, over, in a matter of fact, it's 12.5 years, it's going to form to helium-3, which is useful. Why? I'll show you right now. So some of that is going to go to a neutron plus this helium isotope. And then once you do that, once you have this helium, you can fuse it with a deuterium. And once you do that, you can have this reaction where you have this high energy helium isotope here. And so the goal would be to have this helium-3. So eventually, if you make tritium, you can store it and supply it back to form the actual reaction you want, which is this one, which gives you 14.7 mega electron volts of energy and 3.67 mega electron volts here. And this is actually where the mechanical work is going to come from. This is going to be a charged plasma with 3.67 mega electron volts of mechanical work. to make a direct electrical generation. So I think I have room to add it in here. Yeah, so let's make our Helion opposed flow configuration like this. So that's our Helion reactor. Bit asymmetrical. This is the Helion fusion reactor. We have videos on it, and we'll talk about it in class. Okay. So it's a symmetrical collider. It's not a donut, but it's this two channels meant to collide these two plasmas together. And D plasma? Oh, deuterium plasma. So first, you have this ionization step where what you're going to do is form these two plasma rings, these two plasma energy fields. So this is going to be deuterium plasma. You're going to have the electric field ionization. So it's an ionization by an electric field to form these two opposing plasmas. Then the next step is you're going to manipulate the magnetic field surrounding these two balls and accelerate them towards each other until they merge. So that's the next step. Okay, so next it's going to be magnetic field acceleration and compression. So we start off with some big disks. Then it's going to be magnetic field acceleration and compression. So it's going to be both moving towards the center, but it's also going to get smaller. So instead of these big disks, it's going to be these smaller disks. Due to the magnetic field, they're going to be accelerated towards each other and compressed down to smaller volume. So they started off as these deuterium fuels at the end. You ionize it, energize it with electric field to make it a plasma. And then with the magnetic fields, you're going to move it and force it, accelerate it towards its partner, its colliding partner. Then you're going to accelerate it enough that these two merge and start to meld at such high energies that eventually fusion is going to occur. So then you have a further acceleration to collide and merge these two plasma balls. So it's going to be, where they're going to form the plasma ball, and it's one merged ball that's compressed and merged. Then they're going to ramp up the energy from the outside. Then once it's hot enough and merged enough, once it's merged and hot enough with enough energy induced, you're going to get this fusion process going. And hopefully the fusion reactions that you induce give you more energy out than you put in. That's where our technology is at now, where we have all this design, all this engineering that and then the actual process, it requires so much energy to put in to induce this fusion. We're barely able to achieve this process with a net gain in energy at the reactor level. That's where we are now. Hopefully we can keep on getting better and better to make this a net energy supply with this process. So then, once you have the fusion going and you have the steady supply of H4, what you're going to do is have this direct energy conversion at this stage here. Once you have this helium-4 plasma formed with more energy than you started out with, it's going to supply a force. It's going to literally expand against these magnetic field. So it's literally going to say it's going to be a force plasma pushes onto magnetic field to induce electrical current. So instead of relying on a heat engine where you have to boil water or turn the turbine, here it's this expansion of this gas that's being confined with the magnets. It's going to be an extra energy source where you put on this energy to compress and induce this fusion, but once you convert to this helium-4 by this mass deficit of this these products, which may have a different mass, if they have a lower mass, where did that energy go? It goes into energy. And because you have this extra energy, you can manipulate this gas and allow it to expand somewhat. Because it's going to expand, you're going to be able to feel that force in the magnetic field and induce an electrical current from that, from the response of the magnet. So that is one potential fusion approach to take advantage of these fusion reactions, a fact that you can undergo this process whereby the new atoms are formed, and sometimes you have this imbalance of mass. Where does that energy go? Mass go to energy. So we haven't been able to scale this up into any practical applications yet, but there's a lot of work under these competing technologies, the tokamak, the stellarator, inertial confinement, and the Helion configuration. Those are all up and coming, and there's a lot of engineering, physics, chemistry, and different problems we have to solve and supply. So for here, this is promising because you don't need tritium, and you need helium-3, but it's coming from this fuel. It's not you don't need to fill in the tank of helium-3. You need to get this successful deuterium fusion reaction going and getting some reasonable yield of helium-3 or tritium. So with that, we'll end it off here, and I'll see you guys next time. Thank you.